Hello. All right. So let's see. Two announcements. Remember, I will be here at 4 o'clock, so 5:30, and I might have a few things to review, like maybe 20 minutes. But after that, I expect to answer any questions you ask me. So if you want to go over this problem, we can go over the problem. Or if you want to talk about the slide, we can talk about the slide. But your job is to come with what questions you want to ask. And we will just talk about any of your questions for 1 hour, 30 minutes. Okay? No new ideas, just review. And then also, so let's see. So I'm hearing that everybody is very busy. I think we're going to change some deadlines. So I posted this on the website. So I want to make programming assignment 2 due next Tuesday, not this Friday. So you have a lot more time. But I think you need that one. You need more time because if you're just getting started on it now, it's a little tricky. So you'll probably have to think about how to do it a little bit. So I want to make sure you have all the way until Tuesday. Now, I'm going to keep the written assignments still due every Monday. Okay, so those are all still the same, except we will make written assignment 4, the last one, much shorter. Much shorter. So assignment, 1 was short, 2 was longer, 3 is a little longer, and we'll make 4 short again. So hopefully this is the hardest part of the course. We are right in the middle, and hopefully it starts moving back down again. I think this lecture and the next lecture may be the 2 most challenging topics. So we'll go slow. If you have questions, please ask questions and see how it goes. Okay. So, and I was very impressed that Tsinghua has its own ice cream. CMU does not have its own ice cream. Okay. So last time, we talked about an idea called cache coherence, or memory coherence. And memory coherence was this idea that caches exist in a computer to make copies of the data and keep the copies of the data very nearby, very local to processors. Now, the problem is if you have multiple copies of the data in different caches, when one processor updates one of those copies, then the old copies are out of date. And cache coherence is about making the memory seem like there are no caches there, even though there are many caches in the system. So you may remember this picture, which illustrated how, or one example of how to implement cache coherence. So we had 3 states. Every cache line was either invalid, shared, or in the I want to modify it state, end state. And I think it can be helpful to go over this one more time. So the easiest way for me to go over it is for us to actually think through what the 2 caches are going to do. So just like on the first day of class, I need 2 students to help me with this. So can I have 2 students, please? Can you? And I have another student, please, from the back of the room. Anybody wants to help? You will be a cache. So you are going to be an L1 cache. We need one more L1 cache. Okay, so you just walked in. Yeah. You will have to come to the front of the room to help me with this task. You showed up right on time.
Huh?
Yeah. Okay. So here's what we're going to do. So we have 2 caches. And we are going to carry out this sequence of instructions. So you will be processor 0, and you will be processor 1. Okay? So this is a sequence of instructions which says processor 1 loads and stores some data, processor 2 loads and stores some data. And luckily, I'm going to be memory. Okay? So since I'm memory, I have the values of all the data. So currently, x equals 0 and y equals 0, and that you are processor 1 and 0 and 1, and you have no data in your cache. So you have no data. Make sense? Okay. So we are going to implement this protocol. And for you to be on TV, you need to be in front of this. So maybe if you stand there, it's easier. Okay? So remember the two ideas from last class. The two ideas are, whenever the state of your cache changes, you have to tell everybody. And that if you ever want to write to data, you have to make sure that nobody else has the data. Okay? So let's start working through this. So processor 0 loads x. So you say you want to load x. So I'm memory, and I'm going to give you a copy of the data. And then the question is, what state should that variable, or that value be in the cache? It can be in the, I means not in cache. Invalid means no cache. Shared means I have the data, but someone else may. And modified means I have it, and I want to prevent everybody else from writing to it, or from having a copy. So when you say I want to read the data, what state do you load it into? Shared, right? So we have that. Cache tags. Okay. Now when you said I wanted to read the data, what did you do? Because your friend said, I want to read X. And you have to listen to everything that happens.
Yeah, but I don't have this data, so I...
Correct. So your data was invalid. And you were like, so what? Don't care what you are doing. And it's missing a line, I guess. I guess there's bus read, it should be. Okay. So nothing happens, correct. Now you, okay, so you're next. So good. So you run another instruction. No, it's load. It's still P0. Let's go ahead and make that a P1 load. I don't know what happened. Let's make this. Yeah, otherwise it's not very interesting, I think. So well, actually, it is kind of interesting. Let's go back to this. Okay, let's go back to this. Let's try this. Okay, so now what happens? So you're a processor, and you want to issue a load instruction. Okay, so what happens?
Since I have the data yet,
Yep.
so I won't change.
Correct. Now, do you tell your friend anything?
I'm just
Correct. Yeah, exactly. So this is a cache hit, and the state of the cache did not change. So we don't have to tell anybody anything because everybody else already knows that you have the data in the S state, right? Okay. So what about the next instruction? Store 1 to X.
So I have to change my state from share to the top one.
Correct. So the top one says, I want exclusive access to modify. So you have to say that. You have to say, I want to write.
Yeah, I want to write.
Okay, and so you go, I don't care. And then what will happen is actually, technically in the MSI protocol, I will say, okay, here's the data again, and now you can write. Now, what you were going to do is you were going to say that you already have the data. So maybe I just say, okay, you can write. That's actually the MESI protocol, because you would have had it in the E state, exclusive clean, and then we could have upgraded. But basically, it's the same thing. So memory says, and you say, okay, I realize that you, okay, so what's next? Store X, to 1. So you have to change the value.
Oh,
Yeah. Now remember, I'm memory, I still have X equals 0. Okay? So next instruction, store x equals 2.
This should change.
You already have it modified. Notice that you don't say anything. And you just update the value, x equals 2. Okay? Now I think things get interesting. Ah, yes. So,
I want to write the data, but because I don't have it in cache, and I know this data is modified by perhaps 0.
sorry.
So
Correct. So you have the data, it's invalid in your cache. And you want to write to it. So the first thing you have to do is say, I want to write to the data. Okay? So you're going to say, I want to write to the data.
I want to write to the data.
Good. So now every other cache needs to look to see, do I have the data? If I have the data, which would be I have it in the shared or the modified state, the rules are, if you want to write, no one else can have a copy. So we know that all the other caches have to invalidate their line. They're going to have to move from S to I, or in this case, M to I. Now, what do you need to do? So you need to move to M to I, so you just have to drop the line, literally. But there's one other thing you have to do in this case, because if you just get rid of the cache line, what is the value in memory? Still 0. But the value of x should not be 0, it should be 2. Your value, you have it, right?
Yeah.
So you need to drop the line. If you hear that someone wants to write, you have to flush. So you have to send me the updated value. And now memory is 2. Okay? And now we can complete the transaction. So you go, okay, no problem. No problem. I've dropped the line. You can write now. And now memory will load the value. Oh. What? Oops, sorry, ice cream. but wait a minute. Let's actually be very precise. So you will load the cache line. Because remember, the cache line is 64 bytes. And now you might write one byte or a couple bytes. Now in this case, it might be a little confusing because I only have x equals 2 and not the rest of the cache line. But you have to load the whole cache line, and then you will write the particular value. So you can just keep it going. Okay, very good. Oh, and what state?
State modified.
Modified state, correct. So you do not have the data. You have the data. Memory is out of date again, but the value too. Okay. So now here, P1 load x. So that's you.
I want to read the data, and it's just in my cache, so I don't need to do that.
You don't do anything. You don't tell me, you don't tell him. Nobody gets told because we already don't have the line. And you know that we don't have the line. Why?
Because when I write the data, I have.
Because you have it in M. Because you have it in M, you are guaranteed that nobody else has it. So if you want to read it, read it. Okay. P0, load x. I want to load x. So you hear I want to load x, and what happens?
I will store write the data to memory.
So the first thing you should think, okay, good. The first thing you should think is, well, if you want to load x, then clearly I cannot be in the modified state. I cannot be the only person with the data in it, right? So you could move to the invalid state if you wanted to. But what would be a better thing to do?
I could into the shared.
You could move to the shared state. So you could say, you know what? I'm going to make sure I'm shared, so I'm not going to write to it anymore because I'm not M. And of course, you need to make sure that memory has the most up-to-date copy. So you would flush x equals 3 to here, and now we carry out the memory load, which I don't have enough copies of x equals 3. And you would load into shared, right? So now this is the state of the two caches. Memory is x equals 3, but we don't have it. Okay, so load x. P0 store 4. What happens now?
Since I have to, I want to write the data, so
Yep.
I will create that file.
See. Okay, so you say, I want to write the data, and you hear that, and you say,
So my data is invalid.
yeah, because you cannot keep a copy, because if you ever read that copy, remember, if you read a copy, you don't have to tell anybody, because you're assuming it's up to date.
Yeah.
But the minute he says he wants to write, you can't make that assumption. So just drop it. just drop it. Right. Okay. And now, and notice that why did you not have to write back to memory?
Because I have just one memory.
Well, because it's shared,
Oh.
you know nobody else has made any changes, and that your copy is not modified. So if it's not modified, the value of memory is fine. So I can just give it to you. Okay, so and I did. I did. Okay, so now load store X, P1.
Change to.
Oh, change to 4. Okay. So then you say P1 load X.
So I want to read the data. So
Yep.
use
Okay, and you don't have the data, so you need to get it. So first thing you say is, I need to read the data. You say, oops, I have a modified copy. Okay. So you go to shared. You write the x equals 4 back out,
Yeah.
and apparently I don't have enough copies anymore, so you need that, and maybe there's an S. Yeah, okay. Okay, all right, so then now we're here. Okay, now P0 load Y, not X. Now let's say that Y evicts X from the cache.
Makes sense.
Okay, so now you say I want to load Y.
Yeah.
Now, if you hear I want to load Y, what do you do?
don't do anything.
Correct, because you don't have Y. You have X, but you don't have Y. So I say, okay, sure, you can load Y. Is it a load or so you drop X equals 4, because it's no longer in cache. You have Y, but you'll need your S state. Okay, and now load Y, store Y.
Just move.
So you move to modified, and oh no, that's Y equals 1. There you go. Oops. And then last P1, store Y.
I want to write the data to Y.
So
So
drop
So,
file.
yes. Okay, and you move to, well, you don't necessarily, yeah, so you drop, no, you're right, you drop, because you can't hold it. You send it back to me. Okay,
and then I will drop the data.
you drop X, because that's evicted, and you need, what state is that in?
Data is modified.
Correct, so you have your X on it. Okay, so do you see how this works? Is this diagram here, these are the rules that every cache is implemented. So this is an algorithm that's carried out in parallel by all the caches. And there are two major rules. If the state of your cache changes, you tell everybody else. Because a change in your cache may require a change in somebody else's cache. And then the last rule is whenever you want to write, you tell everybody, and everybody else reacts by making sure that they don't have the data. As a result, there's only one writer at any time, and there's no stale data. There can be many parallel readers. Okay, thank you very much. Okay, so that was very good. Well, that's okay, we will not use that ever again. Okay, so that was, this implementation here was an implementation of snooping cache coherence, which meant we only had a few processors, so it was okay to tell every other processor everything that you were doing. And in the second half of the lecture last time, we talked about a directory-based implementation. And directory-based implementation assumes we might have 32 people up here. And so in the directory, rather than say, I'm going to write X to everybody, you ask the directory, you look up in the book, in the directory, what other processors have X, and then you go talk to them. So we talked a little bit about that last time. And so I had this diagram here where every piece of memory also had the directory keeping track of who had what data. And then right when the bell ended, right when class ended, I said, but this directory can be really big. Right? I said that, well, if we have a 64-byte cache line, and we have 64 nodes, well, that's 64 bits of data to represent who has the data. Or if we have a big computer, 1,000 nodes, if your memory is 1 terabyte, that means you have 2 terabytes to store the directory. That seems a little silly. So I put some links on the web for those that are interested on ways to compress the directory. Like, for example, we pointed out in the class last time that most of the time, very few processors will have a copy of the line. So rather than representing all of the shares as a bit vector, it's actually a lot more useful just to implement them as a list. So if I had 1,000 bytes of data that I wanted to store, I can store either 1,000 pointers, or I can store 1,000 bits, or I can store maybe 10 10-bit pointers to describe the cache line. So there are ways to sort of reduce the cost of directories a whole lot by assuming that the number of shares is sparse. And I put some extra slides here just to let you know, and if you're interested, you could read some of that stuff later offline. So the other thing is that the directory does not have to have a list of processors for every line in memory. And here's why. Because you don't care about every line in memory. You actually only care about what is in cache. So let me give you a real-world example. So this is modern x86. This is a quad-core Intel chip. 4 cores, 4 L1s, 4 L2s, and then 1 L3. That's how it works. And even though this is only 4 cores, this processor right here actually uses a directory-based implementation to do cache coherence. And the way it works is actually pretty interesting, is that notice that there is only one L3 cache for the whole computer. And every piece of data that's in the L2 cache is guaranteed to also be in the L3. So if a processor says, I want to write to my L2, what happens is instead of telling all the other processors, in the L3, that cache line is in the L3. So if it's in the L2, it's also in the L3, because the L3 is bigger. So in the L3, there's actually a little directory for that cache line. And how many bits do I need to store the directory for a cache line? In this case, I only need 4 bits, right? Because I just need to know which L2 cache or which core has the line in it. So the way it works is if this like let's say this cache says, I want to write to the data, just like one of the students. It looks up in the directory, in the L3 directory, and looks up the 4 bits and says, which other processors have the data? And it will send those processors a message. And that's exactly how it works. And keep in mind that like this is one Intel processor. What happens if we have 2 processors? So the computers that you ran assignment 1 and 2 on, they have 2 CPUs, 2 completely different CPUs on one motherboard. And so the interconnect across the motherboard is also sending directory information. So this directory between the 2 cores only needs 2 bits. Because if it misses on this L3, it just needs to tell this L3 that maybe you should drop the line. So you have like this hierarchy of directories that are emerging. Let me give you one more example. So this is Intel Xeon Phi processor. This is a 72-core chip, and it is in a lot of supercomputers these days. So this is you can buy this processor. It's kind of like halfway between a GPU and a CPU. It has 72 cores, 4 threads per core, and 16 wide SIMD. So that's a lot of cores, and the cores are organized into a 6x6 grid. So the network connecting all of these all these processors is not a bus like we talked about in class. It is a mesh. So this tile is connected to this one, is connected to this one, and so on and so on. And they use a directory, very much like we talked about, to actually implement cache coherence over 72 processors. So the way it works is that the nodes are organized in the mesh. Here are all the processing nodes. And that to send a message from one core to another, you always send horizontally, and then you turn once and send vertically. So any message from here to here will always go this direction. A message from here to here will always go that direction. And so the way it works is that, let's say this computer, this processor took a cache miss. So it says, I want to write to, or I want to read X. So what it does is every single address X has a directory entry. And the directory entry is stored randomly in some other node. So it's kind of, you just hash the address to another node. So this processor sends a message to this processor to say, show me who has the data. This processor says, nobody has the data. We'll forward the request to memory. So these yellow boxes are the interfaces to memory. And then memory directly responds with the data to the original processor. So it very much is a directory, and every address in the system, if you just hash the address, you will get one of these 72 regions of the chip, and you ask that region of the chip who has the shares. And I have one mode here. There's another mode of how it works, but it's not that important. But the whole idea of this directory-based scheme is never shout out loud because there are too many people. There's too many processors. So you just kind of look up who needs to know and you go ask them. And it's implemented in many real-world processors today, and it can even be a single chip with a lot of cores. Okay, so that's that. And then, so what I wanted to talk about in the first segment today is a little bit of how coherence is implemented in just a little bit more detail. So hopefully this demonstration helped you understand a little bit. And hopefully a little bit more detail may also help you understand a little bit. So I'm going to talk about implementing these kind of coherence protocols. So here, this is the MESI protocol, not the MSI protocol. And so this is the protocol. It's exactly what we just did. The only difference is, remember, we are differentiating between read-only and other processors have it, and read-only and no other processors have it. Because if I know that I have the data in my cache and no other processors have it, if I ever want to write to it, I don't have to tell anybody. I just immediately elevate and write to it. So let's talk about how a very simple computer might implement coherence. So this is our simple computer. It's very much like one processor, two processors, shared bus. So it's very much like the demo here. Student 1, student 2, and it's a shared bus, which means that only one of the students can talk at a time. And so this bus is going to work like this, is that there was one thing that I did not have you do, is really what happens, because everybody cannot shout at the same time, what really happens is a processor will ask for permission to communicate on the network. The processor say, I would like to send a message on the network. And that's what I have, that's sort of the request. And then the network has someone, kind of like a policeman standing on the corner, that says, okay, you can go now, you can go now, you can go now. And that's the word arbitration. So if we have a single shared resource, if there's someone who is saying, here's, you can use it, now you can use it, now you can use it, that is arbitration. It's like we're coming to an agreement on who can go next. So this sequence says, well, one of the clients, one of the processors, or one of the students will say, may I use the bus now because I need to either read data or I need to tell everybody else that I'm doing something. And then at some point, the network, the bus, will say, okay, you may speak now. And that may, and then the person will say, and then the processor will say, I need to load address X. And that may take a while, right? Because memory may take a long time to respond. So that may take a while. And then later, memory will say, here is your answer. And then the next person can ask for their use of the bus. So it's, I need to use the bus, please. Okay, you may, go ahead. I would like to read address X. Wait. Memory says, okay, here's your data. And then somebody else can now say, I would like to use the bus. So that's how, it's a very simple model of our computer. And so let's think a little bit about what happens when there is a cache miss with a single core processor. The cache has to determine where the data goes in the cache. It needs to check to see if the data is there. If it's not there, it needs to say, I need permission to use the bus. It needs to say, I want this data. It waits for the data, and then it receives the data. Okay. So one thing that we haven't talked about yet is that when one processor says, I'm going to write this data, really what we should have done in this demo is it should have been, I need to write this data, and then the student should turn to the other students and wait for them to say, okay, we don't care, or please wait a minute, I need to flush the data. So whenever one processor says, this is what I'm going to do, it needs to wait for all the other caches to say, okay, we have heard you, and we have taken the appropriate action. And memory needs to also wait and say, well, let's see if any of the caches have it dirty. So it'll be like, I'm going to do this, and then all the other caches go, okay, we're going to do this first. And if you are not a software person, if you're not computer science, and you're more of an electrical engineer or a computer engineer, this might be fairly obvious, but a bus is just a piece of hardware. And the reason why only one person can talk on a bus at once is that it's just a wire. And talking on the bus is sending an electrical signal down that wire. And so if multiple processors are talking, the signals cross and you get garbage. So in this bus, I actually have some wires to encode the addresses, some wires to encode the cache line of data when it comes back, and I have 3 additional wires. And so all the other processors will report their answer using these other wires. Like for example, the shared line says that if all the processors see another processor say, I'm going to read this value, they check their cache, and if they find it in their cache, they make the shared line go hot. Right? So if any of the processors are sending voltage down this wire, well then some processor must have the value in cache. And it's the same thing for whether or not it's dirty and I need to flush. And there's the same thing for whether or not I'm done. So whether or not I'm done is, as soon as somebody says, I need to read X, all the other processors send signal down this line, which says, wait, I need time to look up to see in my cache if I have the data. And then whenever they are done and have made a decision on whether it is shared or dirty, they can turn this line off. So when that line is completely off, then we know that all the results are done. There's another little detail, which is think about all the stuff that needs to happen to handle a write back. So in our example, there was one situation where you had a dirty line X, and you wanted to read Y. So we had to say, we have to kick out X, write X back to memory, and then read the new Y. So even though I drew that as one little line in my picture, that's a lot of steps. And it's sort of unfortunate that you had to write out X before reading Y. Because you would have liked to have just started using Y and let the X happen later. So a very common solution in all processors is not to, the answer is not to write out X and then read Y. It's actually to take X out of the cache and put it over to the side and say, I will write it back later. And I immediately start reading Y so I can continue running my thread. So this is an example of more parallelism in the system. And you can kind of see that in this diagram of the cache. And this is a really old Pentium cache. I think it was a really old x86 processor, I think, that was multi-core. So it looks complicated, but it's actually not that complicated. Here's the actual design. So here's the bus. Here's the cache. The processor's there. And if the processor wants to read data in the cache, it checks these cache tags to see if the data is there and responds. Pretty simple. Now it's kind of interesting that if the processor is busy checking these cache tags, well, the cache can't check those tags to answer any other coherence requests. So if some other processor yells out, I need to write X, and this processor is busy handling a read or a cache hit, then the rest of all the other processors in the system have to wait, because this processor has to check its cache to see, do I have the data to respond to the snoop. So that's actually why they duplicated the tags, so that you can check the cache for snooping in parallel with checking the cache for processor loads and stores. So you see tags here, and so if an address and a command comes on the bus side controller will say, oh, I'll check the cache for this address, and if so, I'll report back the answer. And then here is the write-back buffer. So the write-back buffer is the one cache line that has been evicted from the cache, but the cache just kind of put it aside so we can read more data and start going immediately. So this is the write-back buffer. So things get a little complicated because if you're trying to see is the data in the cache has to actually check the current state of the cache as well as what's in the write buffer to see if this processor has the data. So the details of this are not particularly important. What is important here is that even though I drew like one line, the cache has to do like 8 or 9 different things to actually implement the protocol. There's many steps. So remember in the coherence lecture, I told you that this whole protocol is meant to give us the illusion that all of the memory operations to the same value occur in some sequential order. That's the definition of coherence. All memory operations have some sequential order. But if writing a piece of data involves like 10 steps, there's an interesting question of, given our demo here, when does the write commit? Well, what I mean by commit is, at what point can I put the dot on the timeline? This is the point at which all the processors agree that the write has happened. And by the definition of coherence, any other read after this write, if this is a write of the value 25, any later read must get the updated value. Otherwise, memory doesn't make much sense. So if you think through our two students walking around, working on the coherence protocol, remember during the write, what did I have to do? I had to flush the old line. I had to tell everybody else that I was going to write. I had to load the updated values from memory. And then I had to actually update the cache line. So at what point do you think that the write was actually sort of done? It's Kind of an interesting question, right? Do you think it was when everything was done and I had written the memory? Or sorry, I had updated the cache line? Or do you think it was essentially done when maybe you shouted out, I'm going to write? It's kind of an interesting question to think about. So this question of, well, when does a write commit? And really what I mean by commit is, when do all processors agree that the write is done? Because that's what coherence requires. And a good definition of, well, when do we all agree that the write is done? Well, that's the point that if we ever read the data in the future, we would get the updated value. So in this demo, what was the point where if the second student ever read the value, you were guaranteed that you were going to get the latest information? Like, at what point are you guaranteed that you will get the rate? So if your friend says, I'm going to write, there was a long sequence of steps that had to happen. But at some point in that sequence, you were guaranteed that if you ever did a read in the future, you would get the updated values. Do you know what point that was? So let's think about this. So the core, you issued the store instruction. You looked up the line in your cache, and you noticed there was a cache miss. You needed to shout out to everybody else that you were taking a cache miss. You got access to the bus, and then you said that I'm going to write to this value. Oh, sorry. And then you said, okay, I heard what you said. I will drop the line. Then memory responded with the answer. And then you updated your cache line. So at some point in this process, you are guaranteed that if you ever read the data again, you would get the updated value. Do you know what number after what step that would be? Exactly, right? So right after 4, you have dropped the line, which means that if you ever read the data again, it needs to come from memory. If you ever read the data again, you have to get the bus and shout out to everybody else that I'm going to read the data. And if you ever shout out that I'm going to read the data, you have to comply with the rules, and the rules say that you're going to take that dirty line and flush it out to memory. So after step 4, it is not possible for you to ever read the old value of the data. So virtually, the write happened then. You could take as long as you want to actually do the write. But as long as whenever he asks for the data in the future, you give him the updated value, to him, the write happened right here. And that's actually an important thing. So if I saw this sequence of all these things happening in the computer, both of you would agree that if you had to draw a point of time when the write happened, it would definitely be after step 4. So when I say write commit, I don't mean everything is done. I don't say the instruction is finished. I say that's the point that when we agree, we all agree. And so that's what I have here is the answer to the question that we just talked about. So I will skip through this one. Okay. So we're almost out of time. But I think I'll leave this part of the lecture to another class. This part of the lecture, I didn't know if we would have time, but I think this is the right amount of material. I think we were good. We won't talk about this in lecture. You can read it if you'd like. But all I changed now is when we talked about our simple bus, we said that I make a request, and then we wait, and then memory responds. And so the next couple of slides are all about what happens when we allow parallelism on the bus. Meaning that while I'm waiting for memory to respond, another person can use the bus. So it's actually just pipelining these memory transactions. I'm not going to talk about it. I think it's more detailed than we need, and we'll move on to another topic in the next class.